cost. So now this model can be applied in frameworks like scheduling, network design, and selfish routing. And the last one is the one that we are going to focus today. So let's see a simple example of routing game, the two parallel links, where we have two players, the red and the blue, that both of them uses the top link. The red player has a weight of 1 and the blue player has a weight of 3. So that will give a joint cost on this resource of 64, since the cost function is x cubed. So the question now here is how we will share this joint cost of 64 between these two players. So this is determined by the cost sharing method that we will use. So in general, a cost sharing method, it takes as an input the weights of the users and a cost function, and gives us an output a cost share for each player I. So in this, in our paper, we symbol the cost share of each player by xi of p, where p is the specific outcome. A pureness equilibrium is a state where no player can improve its cost share by deviating to another strategy. By relaxing this definition, I introduce you to the approximate pureness equilibrium, where it's a state where no player can improve by at least a multiplicative factor rho if he deviates to another strategy. Proportional sharing is the most common method that has been applied until now to congestion games. So in proportional sharing, the proportional share of a player, the cost share of a player is proportional to the flow that this player assigns on a resource. So here we have the previous example. So let's focus on player blue. So we see that the fraction of its flow over the total flow of the resource is 3/4. And because of that, the 3/4 of 64, it gives a proportional share of 48 for the blue player. And similar, we can compute the proportional share of 16 for the red player. So we can see that this instance is a pureness equilibrium because no player wants to deviate to the bottom link. So here, if we put both players to use the bottom link, we can see that this is not an equilibrium, because at least the red player, we can see that if he deviates above, then he can reduce his cost share to 1. I continue with the Shapley value. So the Shapley value of a player is the average marginal cost increase that this player causes to the joint cost over all possible orderings of the players. So again, here we have the previous example. And because we have only two players, then we have only two possible orderings, where the red player will be first or the red player will be second. So in the first case, the red player enters first the resource, and we can see that he causes a joint cost of 1 to the resource. And as soon as the blue player enters the resource as well, then this causes an additional 63 in the joint cost. So we can see that this blue area is all the marginal contribution that the blue player causes in the joint cost of that resource. On the other case, the blue player enters first, and that causes a 27 joint cost of 27. And as soon as the red player joins in, then this gives an additional 37 to the resource. So by taking the average of these numbers for each player, then that gives a Shapley value of 19 for the red player and a Shapley value of 45 for the blue player. So now 3 more definitions. So we introduce also the approximate price of anarchy, where it's the worst case ratio of the social cost in an equilibrium towards the optimum. For a class of games, we take the worst case over all instances of this ratio. So we introduce a similar definition to the price of anarchy, but with respect to the potential of a class of games. So, and we call it stretch. So this is the stretch of a potential game is equal to the worst case of the potential value in an approximate equilibrium towards the minimum potential value. So now this definition is more like an introduction to the next one, which we mostly use in the paper. So we define also a stretch which is restricted to a subset of players in a sense that only the players that belong in set A participate in the formation of the equilibrium, and the rest of them, they have a fixed strategy. So what we know until now in congestion games with proportional cost sharing, which, as I said, it was the standard cost sharing method studied until recently, we know that there are games with no pureness equilibrium. We know that there exists approximate pureness equilibrium with, with 3/2 approximate equilibria for concave functions. For polynomial functions, we know that exists D+1 approximate equilibria, where D is the maximum degree of a polynomial. And of special interest to our work is the polynomial time algorithm of Karagiannis, Fanelli, Gravin, and Skopalik, which they compute for linear cost functions a 3 plus root squared of 5/2 approximate equilibria, and for polynomial cost functions, they give a D to the 2 times the approximate equilibria. For congestion games using Shapley values, we know that these games are potential games. So given now that we know that potential function exists, this gives a rise to a natural question of how quick we can reach an equilibrium. So unfortunately, such a process can take exponential many steps, even for the linear unweighted case. And we also know that computing a pureness equilibrium is PLS complete even for the affine unweighted case of congestion games. So now what we do, we relax the notion of pureness equilibrium in the approximate pureness equilibrium, and we compute approximate pureness equilibrium in Shapley value weighting congestion games with polynomial delays. How we do that? We follow and adapt the algorithmic approach of Karagiannis, Fanelli, Gravin, and Skopalik. A few words about this approach. This algorithm, I say again, was developed for proportional sharing. It runs in phases such that the players that participate in each phase experience costs that they are polynomially related. And this is crucial because with that, the authors achieve a polynomial running time. To adapt this framework, someone needs to upper bound the stretch of the potential. However, for this model, the authors, because as we said before, weighting congestion games may not have equilibria, so therefore they do not admit a potential function. So to overcome this barrier, they approximate the weighted congestion games by a class of potential games which they construct and define them as psi games. So using this approximation, they actually prove that an approximate equilibrium in a psi game is also a d factorial row approximate equilibrium of its corresponding weighted congestion game. And at the end, they achieve a final computation of d to the 2 times the approximation in weighted congestion games with proportional sharing. So what is the main difference of adjusting this framework to our setting is that instead of using the potential function of psi games, we work directly on the potential function of our model. So this helps us to significantly improve our final approximation. However, it changes loads of the technical details of the analysis. We also give an upper bound on the A-limited stress. As I mentioned before, this is an important part because this bound is given as a parameter to the algorithm, and is actually, this bound will be actually very close to the final approximation of that the algorithm guarantees. And to do the above, to do this, we prove a series of structural properties for Shapley values and the potential. However, due to the time limit that I have, I'm going to mention only on a high-level proof sketch for the upper bound that we give for the limited stretch. So to do this, one of the main key properties that we prove is this inequality, where we actually approximate the cost, the Shapley value of a player by his corresponding proportional share, and vice versa. Now, this approximation inequality is being used in multiple places in our paper for multiple proofs. It could be a useful tool also for other applications apart from this one. And last thing I would like to mention that the equality here holds for d equals 1. So that means that for linear function, Shapley values and proportional shares coincide. We go back now to the upper bound of the A limited stress. So the proof consists of two parts. So in the first part, we prove, using the approximation equality from before, we prove a technical lemma that states that the A limited stress can be upper bound by this product. So the second part consists of how you can actually upper bound this product. Just to mention that where P hat is the minimizer of the potential. So how we can upper bound this? So it's easy to see that by substituting the potential minimizer from the optimum outcome, that gives directly the definition of the price of anarchy. So now we also prove a second lemma where we actually upper bound more the price of anarchy, and we upper bound it by this ratio. So at this point, I would like to mention that the blue part has been proved for O equals 1 from Gadzelis, Kollias, and Roughgarden for this class of games. And now, substituting this up here, we get the final upper bound, which is this product. So again, I repeat that our final approximation is very close to this amount. So regarding the computation now of the algorithm, we show this theorem which states that an alpha approximate equilibrium in this order can be computed within a polynomial number of improvement steps. So to prove that, we show a series of technical lemmas. However, here I'm going to mention just a high-level proof roadmap, which follows the next steps. So we first we show that we bound the potential of the moving players for each phase of the algorithm. We show that the algorithm uses a polynomial number of improvement steps. We show that after the last phase of the algorithm, every player is in an alpha approximate equilibrium, where alpha equals to 1 plus O gamma times the limited stretch. So gamma is a small positive number. So, but we saw before that the limited stretch in the worst case can take this form. Then we prove that this form is actually in the order of d over ln2 to the d. And we actually show that using this algorithmic approach, you cannot do better than this order. And that was the last part for this theorem. However, until now, we have an algorithm that is polynomial in the number of improvement steps. But in each improvement steps, we have to compute, we may have to compute multiple Shapley values for one player. But to compute that, we know that it's computationally hard. So to overcome this barrier, we use known sampling techniques to compute approximated Shapley values. And then we proceed to the algorithm with these approximated values. So these allow us at the end, after technical analysis, to compute an alpha approximate equilibrium in polynomial time with high probability. Apart from the Shapley value weighting congestion games, we also use our results to compute equilibria for the weighted congestion games with proportional sharing. So we actually show that an alpha approximate equilibrium in this order as well can be computed within a polynomial number of improvement steps. And how we do that? Now we approximate the weighted congestion games by the Shapley value weighting congestion games instead of the psi games of the previous paper. We now lose, using our approximation inequality, we now lose only a factor of d squared, roughly, instead of the d factorial that the previous paper had. And this allows us at the end to give a final approximation guarantee of d over ln2 to the d instead of the d times 2 times d that it was before for this model. And summing up, here is all the results that I mentioned regarding weighting congestion games with Shapley values and our results for proportional sharing. Thank you. Yes.
Is there any understanding of whether that is a continuous function of, I mean, does it degrade gracefully from the price of, it's worse than the price of anarchy, right, for any alpha?
You mean the approximation guarantee?
The price of anarchy. So you talked about the alpha price of anarchy as well, right?
Yes. Trying to remember, yeah. I don't remember. There is, on the paper of Colliers and Garden, there is the exact price of anarchy for these games. I don't remember in what order it is now.
Okay, okay, that's fine. Thank you. Other questions? Okay, so let's thank the speaker once again. So the next talk in the session is going to be by Marc Schroder, and he'll talk about congestion games and variable demands.
Thank you, Omer, and thank you all for being here. So the paper that I'm presenting today is joint work with José Correa and Ruben Hoeksma. You might wonder about the weird combinations of universities, but we conducted this research last year when both Ruben and I were postdocs in Chile. So let me try to motivate our problem by means of the following picture. So the picture is not very clear, but what we have given here is a map of Bangalore, actually. And I asked Google Maps last week, what is the quickest way from the conference hotel, here, bottom right, towards the institute over here, top left? Given that I asked this question last week, Google Maps also didn't know what the actual traffic was going to be like. So what they give us is an interval of times for each of the proposed paths. What we now want to investigate is what is the effect of this variability in travel times on the choices of users. Recently, there has been an increased interest in this question, and most of these models, however, assume that the randomness takes place at the level of the latency functions. So in fact, they assume latencies are random. What we do in this paper is, where does the variability actually come from? Well, it comes from the randomness in demand. So we look at a congestion game with random demand, and we try to see the effect of that on choices of users. And then in the end, we try to find out what are the implications on efficiency. So to be more precise, what is it that we're going to do? We look at a network congestion game or a selfish routing game with random demand. In fact, the game that we look at is a game of incomplete information. So we have a random variable that selects a set of users for travel. Then, not knowing the outcome of this random variable, each of these users have to select a path in the network. The contribution of this paper is not necessarily the model we introduce, nor the proof techniques that we use. It's rather one of a more conceptual nature. That is, recently there was another paper by Wang, Doan, and Chen that looked at a very similar setting. But what they found is that by using their model and the equilibrium concept, the price of anarchy goes to infinity as the variability of traffic increases. What we ever show is that if users minimize their cost based on experienced demand, so based on demand they actually learn through the network, the price of anarchy stays the same as is known for fixed demands models. So in fact, by using our equilibrium concept, the concept we propose, we see that the price of anarchy is robust to random demand. So I'll make all these concepts more clearer in a second. So a quick outline of this talk. First, I'll introduce our model, and I introduce the equilibrium concept that we're going to use. I will try to clarify this by means of an example. Then we look at this alternative equilibrium notion that was used in this paper by Wang, Doan, and Chen, and see why the price of anarchy might go up to infinity as demand variability increases. And then we step back to the observed equilibrium, and we'll look at the main result for this equilibrium concept. So the model. So we have given a non-atomic network congestion game with random demand. So what are the ingredients of this game? We have three main ingredients. First of all, we have a directed network. So we have given some vertices, some directed edges, and each of these edges is endowed with a latency function. So the idea of this latency function is it measures the delay of the users on that edge. Note that we make the standard assumptions on these latency functions. So in particular, we assume them to be non-decreasing. The more users, the longer it takes to reach the next node. Second ingredient, we have a finite set of commodities, and each commodity is defined by a source, so a starting node, a sink, an ending node, and the demand, which is the size of the commodity. So notice that we assume that players are non-atomic. So each player within a commodity is infinitely small, right? They have no effect on delay. So what is the interpretation of a commodity in our model? So a commodity should be seen as a group of users that always travel together. So it could be that two commodities have the same source sink pair, but they might still not always travel together because of the random variable I will talk about in a second. Yeah, so a commodity should be thought of as a group of users with the same characteristics. For example, we could have a commodity consisting of daily commuters, a second commodity consisting of, let's say, university students that only go to university half of the times in the week, right? They only have to be there 3 times a week or so, and so on and so on. Then the third ingredient, this random variable, and we suppose that this random variable is defined over the set of all subsets of commodities. Yeah, so the idea again of this random variable is it selects a subset of commodities, and those are the commodities that are actually playing the game. They're actually going to travel throughout the network. So the probability of S is actually the probability that only commodities K in S are active. Yeah, so in each and every round, it might be a subset of commodities that is selected for travel. Good, so this is the model. So given a flow, so given a distribution of each commodities over its corresponding paths, what is the cost of this flow? Well, we look at total expected cost. That is, for each realization S, so for each subset of commodities, we calculate its total delay, and that we average out over all these probabilities P. And as a standard in the literature, we assume that the optimum flow is a flow that minimizes these total expected costs. Yeah. Okay, then what is this equilibrium concept I've been talking about? We call it the observed equilibrium. Remember, what is our game that we're actually looking at? In the first stage, we have a random variable selecting commodities, subset of commodities for travel. And not knowing the outcome of this random variable, each commodity has to choose a flow over its paths. What we implicitly assume about the behavior of our users is that users learn this random variable when they travel. Okay, so they don't know the exact distribution of this random variable, but they only learn this conditional random variable, conditional on the fact that users are actually traveling. And then we assume, as is in line with Wardrop's principle, that each commodity only chooses paths that minimize these expected costs based on this conditional random variable. Yeah? And that's the equilibrium concept. So users only use paths that have minimum cost based on this conditional random variable. So in fact, this idea is in line with the perfect Bayesian equilibrium of this incomplete information game. So let us actually try to see how this works in an example. Oh. So let us consider this very simple two-link Bigot network. We have two edges. The upper one, which has a delay function of x, which means that the delay on that edge is equal to the amount of flow on that edge. The second one has a constant delay of 1. Now assume we have two different commodities. Both want to travel from S to T, and both have a demand of 1. So the size of each commodity is 1. However, with probability half, it's only commodity 1 traveling, and with probability half, it's both commodities traveling. So note that even though the commodities are defined in a similar way, there is an informational asymmetry between the two commodities. That is, commodity 1, in fact, has incomplete information. Once they travel, they don't know whether commodity 2 is out there, yes or no. With probability half, they're not out there. With probability half, they are out there. Whereas for commodity 2, they know once they travel, commodity 1 is going to be there. So for them, it's actually a complete information game in this particular example. Yeah? And then based on this knowledge, each of the users tries to minimize costs. Or because it's a Wardrop equilibrium, we can actually equalize the cost of two links. So let us do that. So first, this is the cost of commodity 1 of taking the upper edge. What does it consist of? Again, with probability half, commodity 1 is the only one out there. And therefore, as the delay times half times the amount of flow on that path. And with probability half, both commodities are out there. So then the cost is equal to half times both the amount of flows of these commodities. And that has to be equal to the expected cost of the lower path. Remember, we assumed that to have an equal cost of 1. So we want to solve this equation for commodity 1. Then what about commodity 2? Remember, commodity 2 knows that once it travels, commodity 1 is also going to be out there. So it wants the total flow on the upper path to be equal to the expected cost of the lower path, which is 1. So if we solve this set of equations, we find our observed equilibrium. And in this particular case, we can show that in this equilibrium, the first commodity will go up. All users will take the upper path, thereby pushing all other users of commodity 2 to the lower path. Yeah, so because of this informational asymmetry, the users of commodity 1 are taking the upper path. Commodity 2, knowing that the users of commodity 1 are going to be there, therefore are willing to take the lower path. If we then calculate the expected cost of this flow, we get this 3 over 2 over there.
Question.
Yes?
So but you don't allow the fact that maybe I took one edge and then it was very crowded, and now I update and I change my plan route because...
No, we don't allow that. The only thing we allow is that over time you learn these probabilities.
But during the time I'm traveling, I could also learn what the
Sure, that's definitely true. That's definitely true.
But
so the question...
You're not considering that here, right?
No, we're not considering dynamics in that sense, no. What we assume is that that's a good question to investigate actually, whether some of these best reply dynamics converge to the equilibrium concept we propose.
I don't mean
Maybe they do.
Dynamics, I mean that the strategy is more complicated. I just don't choose my path initially. I travel and then I also learn from the first edge.
Ah, okay, so within the network you can update your...
Yeah.
No, we definitely don't consider
And then I come to
that.
a fork and I take the left or the right depending on whether that was crowded.
Now I see your point. No, I don't. No, we don't consider that. It's a static game in that sense, right?
So here each commodity is like a player?
Each commodity is are infinitely many players. I mean, yeah, they do compete, yes, but I mean, so that's what I said in the beginning. So you should think of a commodity as being a set of players with the same characteristics. So they always travel together within the same commodity, but they do compete in a sense, yes.
So, can you explain me the second equation in this observed equilibrium?
Yes, this one you mean?
Yeah.
So remember what was the random demand variable we had? With probability half, it's commodity 1 only, and with probability half, it's both commodities. So from past behavior, let's say, commodity 2 knows that once they travel, commodity 1 will also be there. So what are the expected costs of going up then? Well, it knows that both commodities are out there, so it's a total amount of flow of commodity 1 on the upper path and the amount of flow of commodity 2 on the upper path. So this is the expected cost of going up.
Okay.
And that should be equal to 1, which is the expected cost of going down. So it's because of this, because they know that they're always going to be out there. If they're out there, commodity 1 is also going to be out there.
But these probabilities are not known, I mean, to begin with. I mean, this is just a model right now. Right?
Yeah, so this is not known, but we assume that, I mean, basically they learned the conditional version of these probabilities.
Okay.
So that's why they learned that once they're out there, commodity 2 is also going to be out there. So this is what they learn in the game. So they don't know the piece, but I mean, they know this conditional random variable. That's what they know in the equilibrium. We assume they know that from past behavior.
No, but to begin with, they cannot even write these equations then actually, because you don't know that probability distribution.
Sure. But I mean, it's an equilibrium concept of a static game, right? Sure. The underlying idea is being that they learn. Yes. Okay, obviously, this doesn't need to be the optimal flow. I mean, in this example, you can also calculate the optimal flow, and then you could get down to 5/4. And the main question we want to answer in this paper is, what is the price of anarchy of these games? Can we say something about it? Are they constant? Are they constant for some set of latency function? Yes or no? And we'll get to that answer in a second. But before I go there, I would like to take a small detour, and I would like to look at this alternative equilibrium notion, which was one of the motivations actually to consider this game in the first place. So the alternative equilibrium is one proposed by Wang, Duan, and Chen in 2014. And what they do is slightly different. So their model is also slightly different. They assume that each source sinc pair comes with a random variable, but then over demand levels. Right? So with some probability, demand is 1. With some probability, demand is 2. With some probability. So it's a probability distribution not over subsets of commodities, but over real numbers. Yeah? And they assume that users know these random demand variables and try to minimize paths based on these random demand variables. Moreover, because all users of the same commodity have the same information, we assume them to know the distribution. We assume that all players make the same choice. So all players choose the same unit flow or the same probability distribution over their corresponding sets of paths. So in this example, how does that work? So now we assume that with probability half, we have a random variable. With probability half, we have a demand of 1 unit, and with probability half, we have a demand of 2 units. So then what users try to do is they try to minimize expected costs. So they want to set the expected cost of up equal to the expected cost of down. So what's the expected cost of up now? With probability half, 1 unit of users is out there, and with probability half, 2 units is out there. So they solve the following equation. So their equilibrium gives this flow here. Yeah, notice the difference between their model and our model. In their model, they assume players know the probability distribution. We assume players update the probabilities conditional on the fact that they travel. So why does this go wrong? In the sense that why does the price of anarchy go up if variability increases? Let us consider this very simple example over here. Take some m and assume m is some large number. Then with very high probability, we have a very low demand. And with a very low probability, we have a very high demand. So the bigger m is, the wider the spread of the probability distribution. But on average, this random variable has a demand of 1. That's the way we constructed this random variable. So on average, demand is 1, but the larger m is, the wider the spread becomes. So now, because the average is 1, in the equilibrium, everyone is willing to go up. Yeah, remember what did players do in this users equilibrium of Wang? They minimize expected costs based on this random variable here. So in the equilibrium, everyone goes up. You can calculate the corresponding costs, which are linear in m. But, I mean, you can easily find some other flows. For example, everyone goes down. That has a constant cost. So if m increases, this price of anarchy will go to infinity. Yeah, so clearly this equilibrium concept is not robust to variability in demand, or at least not to large variability in demand. So let us step back now to this observed equilibrium, and let's see how that one performs in terms of the price of anarchy. That brings me to the main result. So before I state the result, I want to step back and to see what we already learned from the fixed demand models. We learned that in general, the price of anarchy could be infinite for fixed demand models, but if we restrict it to a certain class of latency functions, we can say something more. So for example, if we have affine latency functions, we know that the price of anarchy is only 4/3, right? And this can be found by means of this anarchy parameter beta over here. So this was first defined by Tim Roughgarden and Eva Tardar's paper, and later a nicer proof was given by Jose Correa. But what they showed is that this anarchy parameter exactly characterizes the price of anarchy if demand is fixed. So if we put probability 1 on some subset of users, right? So now the question is, what happens if demand is random? In fact, nothing changes at all. The same theorem holds true for this random game as well. So this congestion game with random demand. So in fact, the price of anarchy is independent of the specific random demand variable. So the proof is not very surprising. It follows actually the exact same lines as the original proof. So I will skip that. What is maybe more interesting is the following question. So given that we have the same upper bound on the price of anarchy, and given that this upper bound is tight for fixed demand settings, does randomness then reduce the price of anarchy maybe? Unfortunately, also the answer to this question is no. That is, we can find examples in which each subset of commodity has a positive probability, but the price of anarchy is still equal to 4/3 for affine latencies. And the following example over here specifies that. Again, we have two paths, one with a linear delay, one with a constant delay. The random variable is now what follows. With probability a quarter, it's only commodity 1 out there. With a probability quarter, it's commodity 2 out there. And with probability half, it's both commodities out there. So what do commodities know? With probability 1/3, what is the conditional random variable? With probability 1/3, it's only them out there. With probability 2/3, they also see the other commodity out there. So they solve the following set of equations. Calculating the equilibrium then gives us a cost of 5/2. You can also easily calculate the optimal flow, gives us a cost of 15/8. If we divide these two, we get exactly this ratio of 4/3. Yeah, so randomness also doesn't decrease the price of anarchy. Okay, let me conclude. What have we seen? We've proposed a network congestion game with random demand, in which players calculate cost based on the conditional random variable of traveling. And our main result is that the price of anarchy is robust to this random demand. In fact, the price of anarchies seem to be the same as for the fixed demand setting. And in this talk, I only talked about non-atomic congestion games, but in fact, the result is more general than that. It can be extended to any game within this class of smooth games. So for example, the known upper bounds on price of anarchy for atomic players or atomic splittable players, those bounds can also be extended to a random demand version of these games by using exactly the same procedure as proposed over here. Good. I would like to thank you for your attention, and I'm looking forward to any questions that you might still have. Yes.
So in your model, all the agents are effectively trying to minimize their expected cost.
Yes.
What if you try to introduce some sort of like risk aversion in your specific model? Do you know if things can get better or worse?
What do you want to do?
If you add risk averse agents, or let's say
risk averse agents. Yeah, we thought about the question, and I mean, given that especially recently there are many models that try to incorporate this risk aversion, but I don't think the results will be much different from the results in those papers. So you would get different price of anarchy bounds, but yeah, I don't think it's, yeah, I don't know. I don't think there is any new insights over the models that already have been proposed, but I'm not 100%.
But your source of uncertainty somehow is different then?
Yes, exactly. Yeah, you have to incorporate the fact that players are risk averse, so then optimal flows will change as well as equilibrium flows will change, definitely.
More questions? Okay, so if not, let's thank Marc once again.
Okay. So, hello all. My name is Omer Ben-Porat. Multitasking is not my deal. I'm from the Technion, Israel Institute of Technology, and today I'm going to present a joint work with my advisor, Professor Moshe Tennenholtz, called Shapley Facility Location Games. So, since the seminal work of Hoteling almost 90 years ago, facility location games have been a topic of major interest in operation research, computer science, and economics. So, before I go on with our model, let me just briefly state the basic elements of facility location games. We have a set of users who are distributed in some metric space. They can be referred to as customers or voters if you wish. There's a set of players who select their facilities, location, or points in the user space. Facilities can be associated with political agenda, product properties, or physical location of a store. Users are attracted to these facilities, and the payoff of each player is the proportion of users who are attracted to her facility. So what usually assumed is that users are deterministically attracted to their nearest facility, and this is what we reconsider in this paper. So irrational decision-making is basically everywhere, and Kahneman and Tversky demonstrated that in their seminal work. They won a Nobel Prize for it. Also, we have the satisficing principle, which is due to Simon, who said that decision-makers can satisfy either by finding optimum solutions for a simplified world or by finding satisfactory solutions for a more realistic world. And this is, as I said, what we do in this paper. We introduce a non-deterministic decision-making process for the facility location game, and then we analyze the induced game. Okay, so this is our model. We call it Shapley attraction function due to a surprising connection to the Shapley value, which I will be describing in the next few slides. So each user is doing the following. First, he samples his satisfaction threshold from the uniform distribution, and afterwards he selects one facility with satisfaction level above that threshold, if such a facility exists. So let me illustrate that. We have this user right here, and he has given the location of the players. The players have already selected their locations, and he has 3 offers with satisfaction levels 0.3, 0.5, and 0.7, and then he samples this satisfaction threshold. Now, if the satisfaction threshold is between 0 and 0.3, then all facilities satisfy him. If it is between 0.3 to 0.5, then only the orange and the yellow facilities satisfy him. And if it is between 0.5 and 0.7, the yellow facility will satisfy him. Above that, none of these facilities will satisfy him, and therefore he would skip all offers of the players. So basically, this simple and intuitive decision-making process defines it pretty straightforward to see that we can compute what's the probability of that user to be attracted to, for example, the orange facility. And this function mu, which computes the attraction probabilities, this is what we call a Shapley attraction function. And this asterisk here says that it is not necessarily the uniform distribution. You can just plug in which distribution you like, and I only used uniform distribution for this example. So now I'm ready to introduce the model formally. We have a compact set of users and some density function over that space. There is a satisfaction function which maps 2 points to location in the user space into a point in the unit interval. We do not assume anything about this satisfaction function. Besides, it should only be Riemann integrable. And natural such functions are continuous or step functions. We have n strategic players, and users are attracted to the facilities according to the Shapley value I presented in the previous slide. And the payoff of each player is essentially the expected number of attraction to her facility. Okay, so here's a toy example. Let's focus on user space, which is the unit interval, and uniform distribution over that space, 2 players, and let the satisfaction function, be 1 minus the distance. Now, those of you who are familiar with hoteling game, with the pure hoteling game, this is essentially it, except from the attraction function being the Shapley attraction function. Now, this game possesses a pure Nash equilibrium, which is 3/8 and 5/8, completely different than what you would have get in hoteling's model. Great. So let me talk about our results. The first result is that Shapley facility location games are potential games, and we proved that by showing a potential function for this setting. And since the strategy space of the players and the payoff functions are strategy space of the players is compact, and the payoff functions are continuous with respect to the strategies, then as a corollary of the seminal paper of Monder and Shapley, we get that every Shapley facility location game possesses a pure Nash equilibrium. And this refers to the setting to the model in its full generality, right? High dimensional space, any number of users, any satisfaction function, and any density over that space. And also, this is in sharp contrast to hoteling games, where even for the restricted case of unit interval, uniform distribution, and 3 players, which is known to have no pure Nash equilibrium. Okay, so after establishing the existence of a pure Nash equilibrium, it is interesting to ask how fast does the learning dynamics likely to converge. And we focus on the multiplicative epsilon pure Nash equilibrium concept. What we show is that after at most O of n log n over epsilon times log of something that was referred to as stretch in earlier presentation, this number of iterations, the player will converge to a pure Nash equilibrium, or to approximate pure Nash equilibrium. And this is in the spirit of Chen and Sinclair, 2007. And we also show in the paper that in some cases it is reasonable to assume that player can, or it is reasonable to assume that approximate best response can be computed efficiently by the players. Great. So the price of anarchy, or the loss due to strategic behavior. So we have 2 seemingly different objective functions in mind. There's the objective function of the players, the social welfare of the players, which equals to their sum of payoffs. And there's the social welfare of the users. Arguably, one natural such social welfare function is the expected number of attractions. And this approach was also adopted by Feldman et al. In a recent AAAI paper. They call it participation rate. Now, in our setting, these 2 terms actually coincide. So any improvement on the social welfare of the players implies an improvement in the social welfare of the users. And what we show is that the price of anarchy is bounded by 2n minus 1 over n, and we also provide a game instance achieving this bound. So in order to complete the picture, I now owe you an explanation about why I keep on bringing up Sir Lloyd Shapley value's name. So here's the relation to the Shapley value. Imagine a user puzzled by all the offers of the players, and one way to decide how to assign the attraction probabilities is to consider all the players as being collaborative and just distribute the probability of being attracted in some fair manner among them. So if we look at infinitesimal user, infinitesimal cake, okay, U, and given a strategy profile X, we define the characteristic function VU of C given X, where C is a coalition or a subset of players, to be the maximum satisfaction level that U can have for one of the facilities offered by the players in the coalition C. So we showed that the Shapley value of player I in this cooperative game is essentially the probability that U will be attracted to player I given the strategy profile X. And if we integrate over all such infinitesimal cakes, we get one larger cake. And if we define a larger cooperative game V, which is the weighted sum over those infinitesimal cakes, this is simply by linearity or fixing these values, we get that the Shapley value of player I is essentially his payoff function in the non-cooperative game. Right? So this is the connection to the Shapley value, and the reason we call it Shapley facility location games. To conclude, in our setting, a pure Nash equilibrium always exists, even in the most complex settings. As I said earlier, high dimensional space, any number of players, density function, and so on. We also introduced this simple and intuitive decision-making process and showed one interpretation of it being fair to the players. What we have in mind when we did this work is a competition between clustering parties, where each player I, for example, can select KI facilities, and it turns out that some of our results also extend to this case, carry on to this case as well. In particular, the pure Nash equilibrium exists in this case, and so it can be seen as some sort of early example of competitive clustering, right? And as for future work, we plan on identifying the set of attraction functions which induce a game possessing a pure Nash equilibrium under some mild assumptions, for example, monotonicity, symmetry, and so on. And that would be all. Thank you.
Questions?
So given your last result, given the connection to the Shapley value, aren't the previous result regarding existence, potential function, aren't all these corollaries of the last result?
To the best of my knowledge, it cannot be concluded from this connection.
The fact that you have a Shapley cost sharing.
To the best of my knowledge, at least.
Do you have any natural interpretation about the potential function?
Yeah, it is an exact potential. We show the specific function.
Yeah, but like, do you have any interpretation and so like meaning for this?
It is standard. It is the standard potential function. To be honest, it's pretty much straightforward. You know, sigma 1 over all the congestion functions. I think I have it here somewhere. Probably not. Yeah, so this is the potential function. Right, so as I said, it's pretty standard. Just a second.
If not, let's hand the speaker and all the speakers.
Yeah, just a couple of announcements. So as like yesterday, we'll have the lunch session in the main guest house lawns. Just one alert. Yesterday we had 2 counters, one in the open lawns area and another in the enclosed space. Today both the counters will be in the open lawns area. Secondly, I think we would like to invite you all for a photo session in front of the Tata statue at 2:15 p.m. It would be wonderful if you are here by 2:10 or so. And then the keynote talk by Professor Vijay Vajirani will be at 2:30. Thank you.